In the vast expanse of space, an enigmatic visitor, 30 Atlas, speeds through our solar system. This interstellar traveler defies the sun's gravity, sparking intrigue and caution. NASA assures no threat, yet the United Nations designates it a planetary defense target. Both perspectives hold validity. The object, roughly 300 meters wide, gleams with an unusual metallic sheen, unlike anything in our solar system. So before we go deeper, hit like, subscribe, and tell me in the comments what you think this really means. And if you want to help this message reach others who still wonder, share it on X, Facebook, Reddit, or even just in your group chats. You're the reason this search is alive. Thank you for keeping your eyes open. Travelling at over 95,000 kilometers per hour, it could traverse Earth's diameter in under 30 minutes. Its hyperbolic trajectory confirms an origin far beyond our solar system, making it the first observed interstellar object up close. Yet its behaviour remains unpredictable. Unexplained accelerations cause deviations from expected paths, baffling astronomers. Theories like undetected outgassing or unknown celestial influences fail to fully explain these anomalies. This isn't fiction. It's unfolding in December 2025. The countdown is real, and 30 Atlas's mysteries could reshape our understanding of the universe. Scientists worldwide analyze data from observatories like Chile's Large Synoptic Survey Telescope and Hawaii's Pan-STARRS Array. Space agencies, NASA, Roscosmos, the European Space Agency, and China's National Space Administration are collaborating on an unprecedented scale. Satellites and telescopes track the object, yet the more they uncover, the deeper the mystery grows. Named after the Greek Titan who bore the world's weight, 30 Atlas embodies humanity's potential and fragility. As it races across the sky, captured by amateur astronomers, it evokes awe and unease. The world waits, hoping for answers that may remain elusive. Part 1. The Visitor. What do we know for certain? Its journey began in the unimaginable depths of space, likely tens or even hundreds of light years away, in a region of the cosmos far beyond the reach of human exploration. Its discovery was not a dramatic event, but a quiet, methodical process. On June 12, 2024, astronomers at the Pan-STARRS Observatory in Hawaii detected a faint, moving object in the outer solar system. Unlike its predecessors, however, 30 Atlas would make a much closer approach to Earth, passing within 0.2 astronomical units, roughly 18 million kilometers, on December 19, 2025. For context, this is about 47 times the distance between Earth and the Moon, close enough to observe, but far enough to ensure no gravitational disruption to our planet. Its physical characteristics are equally intriguing. Early observations suggest 30 Atlas is roughly 200 meters in diameter, smaller than Borisov, but larger than Oumuamua. Its surface is dark, reflecting only about 4% of the sunlight that hits it, and its coma, the cloud of gas and dust released as it warms, stretches over 100,000 kilometers into space. This coma is what gives it its distinctive appearance in telescopes, a faint, ghostly glow against the blackness of space. As it approaches the sun, this coma will grow, shedding more material into the solar system and leaving a trail that will linger long after the comet itself has departed. Interpretation. NASA maintains that this is a natural object, a comet doing what comets do, releasing gas and dust as it warms near the sun. No danger, no risk, just another visitor from the void. The agency's public statements have been consistent. 3.2. Atlas is an ordinary interstellar comet, its behavior fully explainable by existing models of cometary activity. NASA's confidence is bolstered by data from the Hubble Space Telescope and the James Webb Space Telescope, both of which have been tracking the object since its discovery. These observations reveal a familiar composition: water ice, carbon dioxide, and trace amounts of other volatile compounds, all of which are typical of comets both within and outside our solar system. However, the story doesn't end there. While NASA's assessment is clear, other organizations have taken a more cautious approach. The European Space Agency, ESA, and the International Astronomical Union, IAU, have both issued statements acknowledging the comet's unusual trajectory and proximity to Earth, though neither has contradicted NASA's classification. More significantly, the United Nations Office for Outer Space Affairs, UNOOSA, has activated its planetary defense protocols for the first time in history, specifically targeting 3.3 Atlas. This decision, announced quietly in a press release on October 15, 2025, has sparked a wave of speculation and concern among astronomers, policymakers, and the public. Speculation. But why, then, has the United Nations activated its planetary defense network for the first time in history, targeting this very object? Why is this comet, deemed harmless by NASA, the focus of a global monitoring campaign that runs until January 27, 2026? The UNOOSA's official statement provides few answers. It describes the activation as a precautionary measure and a routine exercise designed to test the coordination of international observatories and defense systems. Yet the timing and focus of this exercise are anything but routine. The Planetary Defense Network, established in 2013, has never been deployed for an interstellar object before, let alone one that NASA has already deemed non-threatening. The discrepancy between NASA's reassurances and the UN's actions is striking. While NASA's public messaging emphasizes the comet's ordinary nature, the UN's activation implies the possibility of an unforeseen risk. This contradiction is not lost on the scientific community. In private correspondence, several astronomers have expressed surprise at the UN's decision, with one describing it as overkill for a comet that shows no signs of deviating from its predicted trajectory. Others have speculated that the UN may be responding to classified data or concerns that have not been made public. The clock is ticking. December 9 is the first major data check-in. December 19 is closest approach to Earth, and January 27 is the final assessment. These aren't vague future dates. They're concrete milestones counting down now. Each of these dates represents a critical moment in the observation and analysis of 3.3 Atlas. On December 9th, astronomers will gather data from observatories around the world to refine the comet's trajectory and composition. On December 19th, as the comet makes its closest approach to Earth, ground-based telescopes will have their best opportunity to study its surface and coma in detail. And on January 27th, the UN's planetary defense exercise will conclude, presumably with a final assessment of the comet's behavior and any potential risks. What happens in those windows will matter, not just for the object, but for us, because this contradiction isn't subtle. It's right there in plain sight. NASA says no threat. The UN treats it as a target. Both are documented. Both are official. Both are happening simultaneously. The tension between these two perspectives is palpable and it raises questions that go beyond the comet itself. What does the UN know that NASA doesn't? Or, more troublingly, what does the UN know that it isn't sharing? And the question that haunts this mystery is simple. Why? Status update. What we know, 30 Atlas, is an interstellar comet on a hyperbolic trajectory. NASA says it poses no threat. The UN has activated planetary defense protocols to monitor it. What we don't know. Why the UN chose this object for its exercise. Why the exercise extends 5 weeks past closest approach. What the comet's unusual behavior means, if anything. The stakes are higher than they seem. If 30 Atlas is truly just a harmless comet, then the UN's activation is a puzzling overreaction, one that could erode trust in international space governance. But if there's more to the story, if the comet holds surprises that NASA hasn't accounted for, then the consequences could be far-reaching. The comet's trajectory will take it within 0.2 AU of Earth, close enough to pose a risk if its behavior changes unexpectedly. While the probability of such an event is low, the potential impact is high, making the UN's precautionary measures seem less like an exercise and more like a genuine act of defense. In the coming weeks, as the comet draws closer, the world will be watching. Telescopes will track its every move, satellites will monitor its emissions, and scientists will scrutinize every piece of data for signs of the unexpected. And beneath it all, the question will linger. What if we're wrong? What if the Atlas is not just a visitor, but a harbinger of something more? The answers, if they exist, are hidden in the dark expanse of space, hurtling toward us at 30 kilometers per second. The countdown has begun. Part 2, Timeline of a Mystery. November 27th, 2025. The United Nations International Asteroid Warning Network, IAWN, launches Exercise 8, designating 30 Atlas as the target for coordinated global observation. Hundreds of observatories, from the snow-capped peaks of Mauna Kea to the arid plains of the Atacama Desert, activate data-sharing protocols. Telescopes hum to life, their lenses trained on the distant speck of light hurtling through the cosmos. The countdown begins, not just for a scientific exercise, but for an encounter that will captivate the world. Late November. Reports surface of unusual activity. The comet pulses with a 16-hour heartbeat, brightening and dimming with clockwork regularity. Astronomers, huddled in dimly lit rooms filled with the glow of screens, debate the cause. Is it rotation, outgassing, something else entirely? Theories clash as quickly as emails flood inboxes, each scientist eager to unravel the enigma unfolding in the night sky. As November wanes, the comet's pulsations grow more pronounced. Amateur astronomers, bundled against the chill of night, capture the phenomenon on modest backyard telescopes. Their images flood social media, a blurry, glowing object flickering like a distant candle flame. The public begins to take notice. Forums buzz with speculation, hashtags trend, and the comet earns a nickname, the Pulsar. December 1st. News outlets pick up the story. CNN interrupts its broadcast with breaking news footage of the comet erupting, spewing jets of material into space. Brightness surges by a magnitude of 2.5, making the object visible to the naked eye even in light-polluted cities. People gather on rooftops, craning their necks to catch a glimpse of the celestial spectacle. The comet is no longer just a scientific curiosity. It has become a global phenomenon. December 3rd. The European Space Agency, ESA, releases a statement expressing concern. The comet's behavior defies known models. Its trajectory, initially stable, shows subtle deviations as if nudged by unseen forces. Scientists at ESA's Space Situational Awareness Program hunch over screens, recalibrating algorithms to account for the anomalies. The world watches, unaware of the quiet unease spreading through the scientific community. December 5th, a video goes viral. Filmed by a teenager in Sydney, it captures the comet pulsing in real time, its light casting an ethereal glow over the cityscape. The footage is hauntingly beautiful, yet unsettling. Conspiracy theories emerge, fueled by the comet's unpredictable behavior. Is it a natural object, a weapon, a sign of something greater? December 7th. NASA's Deep Space Network detects something extraordinary. The comet is emitting a faint, repeating radio signal. The pattern is complex, almost mathematical. Scientists at the Jet Propulsion Laboratory work around the clock, decoding the signal's structure. They find no obvious explanation, but the implications are staggering. The world holds its breath. December 9th. The mid-campaign check-in. IRWN compiles data from observatories worldwide. Trajectory models are updated, reflecting the comet's erratic path. Behavior patterns are assessed, with the pulsations and radio signals now at the forefront of discussion. Decisions are made about what to focus on during closest approach, just days away. But why December 9th? Why not wait until after closest approach, when the data is complete? The urgency is palpable, though unspoken. Something about 3-2 Atlas demands immediate attention. In conference rooms across the globe, scientists debate the comet's mysteries. Their voices echo through empty corridors, a symphony of curiosity and concern. The comet's trajectory, pulsations, and radio signals defy easy explanation. Yet one question looms above all others. What will happen when it draws near? The clock ticks on, counting down to an encounter that promises to redefine our understanding of the universe, and perhaps ourselves. Part 3, Closest Approach. December 19th, 2025. Closest approach. The comet swings past Earth at its nearest point, still a staggering 7.2 million miles away, but closer than it will ever be. Astronomers worldwide hold their breath as every major telescope locks on, from the towering observatories of Mauna Kea to the icy facilities in Antarctica. Spectroscopy probes the comet's chemical composition, revealing traces of water ice, carbon dioxide, and complex organic molecules that hint at the building blocks of life. Photometry captures the comet's brightness, which surges as it reflects the sun's light, while radio observations listen for any unexpected emissions. Radar, if feasible, will map the comet's surface, searching for craters, ridges, and signs of activity. This is the data collection moment that justifies the entire exercise, a fleeting window to scrutinize a visitor from the outer solar system. But this isn't the end. It's just the peak. The exercise continues through late December into January, all the way to January 27th, more than 5 weeks after the comet has passed Earth and is heading back out into interstellar space. By then, the comet will have receded to over 100 million miles away, its brightness fading to a mere pinprick in the night sky. Yet the observations persist, meticulous and unyielding. Teams of astronomers working in shifts will analyze the comet's trajectory, velocity, and any changes in its composition as it retreats. Ground-based telescopes will collaborate with space-based observatories like the Hubble Space Telescope and the James Webb Space Telescope, ensuring no detail is missed. Why monitor something for 5 additional weeks after it's already gone past us? The extended observation period is not mere protocol. It serves multiple critical purposes. First, it allows scientists to track the comet's behavior as it moves away from the Sun, providing insights into how solar radiation affects its structure and composition. Second, it offers a chance to detect any delayed outgassing or fragmentation events, which could occur as the comet cools and its ices sublimate. Finally, the data collected during this phase will help refine models of cometary dynamics, improving our understanding of these enigmatic objects and their role in the solar system's evolution. Observation. In the days leading up to closest approach, the comet's coma, the glowing envelope of gas and dust surrounding its nucleus, expands dramatically. By December 19th, it spans over 100,000 miles, larger than the planet Jupiter. The coma's blue-green hue, visible in high-resolution images, is a telltale sign of the presence of diatomic carbon, C2, and cyanogen, Cn, molecules that glow under ultraviolet light. As the comet approaches, its tail stretches out behind it, a wispy streak of dust and ionized gas pushed by the solar wind. The tail extends for millions of miles, a ghostly apparition against the backdrop of the stars. Interpretation. The comet's behavior during closest approach reveals much about its origins and history. Its high velocity, over 100,000 miles per hour, suggests it originated in the Oort cloud, a vast reservoir of icy bodies far beyond the orbit of Neptune. The composition of its coma and tail, rich in primordial materials, supports the theory that comets are remnants from the early solar system, frozen time capsules that have remained largely unchanged for billions of years. Its trajectory, a long, looping arc that will eventually carry it out of the solar system, indicates it is a first-time visitor, making a single pass through the inner planets before disappearing into interstellar space. Speculation. Could the comet fragment as it approaches the Sun? It's a possibility that keeps astronomers on edge. Comets are fragile objects held together by a delicate balance of gravity and ice. As the Sun's heat penetrates the comet's nucleus, it can trigger outbursts of gas and dust, weakening the structure and potentially causing it to break apart. If this happens, the fragments could spread out along the comet's orbit, creating a spectacular display of multiple tails and comas. However, such an event could also complicate observations, as the fragments would need to be tracked individually, each one providing a unique data set. Status update. What we know: the UN exercise runs from November 27, 2025 to January 27, 2026. December 9th is the mid-campaign check-in, a critical milestone where teams will review their findings and adjust their strategies. December 19th is closest approach, the pinnacle of the exercise, when the comet will be at its most visible and accessible. What we don't know. What the December 9 check-in will reveal. Will the comet's composition match expectations, or will it surprise us with unexpected elements? Will it remain intact, or will it fragment under the Sun's relentless heat? And what insights will the extended monitoring period provide as the comet recedes into the cosmic abyss? Only time and the data will tell. Part 4. The Anomalies. The heartbeat, a 16-hour cycle of brightening and dimming, defies typical comet behavior. Imagine the contrast on a spectrograph. precise peaks and valleys, each a testament to an unknown mechanism. This rhythm allows astronomers to predict fluctuations down to the minute, an unprecedented phenomenon. What could cause such regularity? Brightness variations are stark, with Hubble observing up to 30% fluctuations in visible light, confirmed by Keck's infrared data. These spikes correspond to temperature changes of over 100 degrees Celsius within hours, a roller coaster of extremes. 30 Atlas pulsates with an internal rhythm, defying expected icy body behavior. Its brightness variations create visible pulsations in long exposure images, a cinematic flicker against the cosmos. Nickel vapor in the coma defies explanation. At 800 million kilometers from the Sun, solar heat can't vaporize nickel, requiring temperatures exceeding 1450 yards C. Yet it comprises 0.5% of the coma's composition. Astronomers speculate about an unseen heat source, a radioactive isotope or unknown chemical reaction. This suggests a process akin to heating in differentiated asteroid cores, yet 33 Atlas shows no such structure. Inverted CO2 to water ratio. Unlike normal comets, 33 Atlas releases more carbon dioxide than water. Rosetta's data on Comet 67P established a baseline of 70% water ice and 20% CO2. For 30 Atlas, the coma is dominated by CO2, with water ice less than 10%. This inversion challenges comet formation models and suggests an origin in a colder region, perhaps beyond the Kuiper belt. Observation. The CO2-rich composition suggests an origin in a colder region. Yet the comet's orbit contradicts this. Its trajectory doesn't align with known long-period comets from the Oort cloud or Kuiper belt. Speculation. Could this ratio result from a past collision or fragmentation event, reflecting the inner layers of a differentiated object rich in CO2? The comet's steeply inclined orbit hints at a violent past. These anomalies defy models. The heartbeat, nickel vapor, inverted CO2 to water ratio. Each challenges our understanding of cometary behavior. Together they raise questions beyond conventional astronomy. The anomalies are interconnected puzzles, possibly pointing to a thermal history far more complex than any comet observed before. The comet's trajectory is intriguing. Its steep inclination, angled at 104 degrees relative to the solar system's plane, suggests an origin outside the solar system or a past gravitational interaction. Its unusually high albedo makes it 3 times brighter than typical comets. This brightness, combined with its pulsations, creates a spectacle visible even to amateur astronomers. The anomalies of 30 Atlas are clues to processes or histories our models can't explain. Each observation builds evidence that this comet is unlike any other. Whether it's a product of rare natural phenomena or something more extraordinary remains to be seen. But one thing is clear. 30 Atlas is rewriting the rules of what it means to be a comet, forcing astronomers to rethink the boundaries between comets, asteroids, and interstellar objects. Part 5. The fragmentation question. Comets often fragment after perihelion, the point of closest approach to the Sun. This is a spectacle that has been observed countless times in astronomical history. The thermal stress of passing close to the Sun weakens their structure, as temperatures can soar to over 1,000 degrees Celsius. The intense heat penetrates the comet's surface, vaporizing subsurface ice, and the resulting pressure builds up until it exceeds the comet's structural integrity, causing it to blow apart. This process can be dramatic, with fragments scattering like cosmic shrapnel. each piece glinting in the sunlight as it trails away from the main body. The most famous example of comet fragmentation is Comet Shoemaker-Levy 9, which broke into 21 distinct pieces after passing too close to Jupiter in 1992. The gravitational forces of the gas giant tore the comet apart, and the fragments later collided with Jupiter in 1994, leaving dark scars on the planet's atmosphere that were visible for months. Another striking example is Comet Ison, which disintegrated as it approached the Sun in 2013. Its brightness surged as it neared perihelion, only to fade rapidly as the comet crumbled under the Sun's intense heat. These events underscore the fragility of comets and the extreme conditions they face during their solar encounters. Will 30 Atlas fragment? This is the question that keeps astronomers awake at night, poring over data and debating possibilities. Some observations suggest it might follow the fate of its predecessors, breaking apart in a fiery display of cosmic destruction. Others hint at a more resilient structure, one that could withstand the furnace-like conditions near the Sun. The data isn't conclusive yet, and the uncertainty adds to the tension. The exercise extends into January, with teams around the world watching for delayed fragmentation or structural changes. Every telescope trained on Theta Atlas becomes a silent sentinel, recording subtle shifts that could signal the comet's demise or survival. If it fragments, it's a natural comet behaving as expected. The cosmos will witness another instance of celestial disintegration, a reminder of the relentless forces at play in our solar system. But if it stays intact, that's harder to explain. That means the structural integrity of Theta Atlas exceeded current models, suggesting that whatever this object is made of is stronger or more cohesive than expected. This outcome would challenge existing theories about comet composition and behavior, forcing scientists to reevaluate their understanding of these icy wanderers. Observation. From a purely visual standpoint, the fragmentation of a comet is a breathtaking event. The once solid nucleus dissolves into a cloud of debris, each piece reflecting sunlight like a tiny ephemeral star. The fragments often trail behind the main body, stretching out into a long glowing tail that can span millions of kilometers. This tail, composed of dust and gas, shimmers against the blackness of space, creating a spectacle that has captivated astronomers for centuries. However, the beauty of fragmentation is tempered by the loss of scientific opportunity. An intact comet provides a wealth of data about its composition, origin, and history. Once it fragments, much of that information is lost, scattered across the void. Interpretation. The behavior of Planetary Atlas raises questions about the fundamental nature of comets. If it survives perihelion intact, it could represent a new class of comets, objects with unusual strength and durability. This would have profound implications for our understanding of the solar system's formation. Comets are believed to be pristine remnants from the early days of the solar system, their icy cores preserving the chemical signatures of that ancient time. A comet with exceptional structural integrity could suggest that some regions of the solar system were capable of forming more robust objects than previously thought. Alternatively, it could hint at an external influence, a process or material not yet accounted for in current models. Speculation. One intriguing possibility is that 33 Atlas contains an unexpected abundance of metals or other binding agents that give it greater cohesion. Some theories propose that comets could have incorporated metallic compounds during their formation, which would act like a skeleton, reinforcing their structure. Another idea is that the comet's composition includes organic polymers, which could form a sticky, tar-like substance that holds the object together under extreme conditions. These hypotheses are purely speculative at this point, but highlight the excitement and mystery surrounding 32 Atlas. Status update. What we know, 32 Atlas has displayed unusual behavior, including a 16-hour brightness cycle that defies easy explanation. The presence of nickel vapor at unexpected distances from the Sun suggests a composition unlike any comet observed before. Its inverted CO2 to water ratio further deepens the mystery, challenging the established patterns of cometary chemistry. The comet may or may not fragment after perihelion, and the outcome will shape the direction of future research. What we don't know, what's causing the anomalies, whether the comet will survive perihelion intact or succumb to the Sun's relentless heat. What the extended monitoring period will reveal. Will it unravel the secrets of 32 Atlas, or will it leave us with even more questions? The cosmos, as always, holds its answers close, forcing us to wait and watch as the drama unfolds. Part 6. The James Webb Space Telescope. Between late December and early January, the James Webb Space Telescope, JWST, positioned 1.5 million kilometers away at Lagrange point L2, will observe 32 Atlas post-perihelion. Launched in December 2021, this $10 billion telescope features a 6.5-meter gold-coated beryllium mirror with 18 hexagonal segments, optimized for infrared detection. Sensitivity, up to 100 times greater than Hubble, makes it ideal for studying the third Atlas's surface temperature, chemical signatures and structural features undetectable from Earth. A tennis court-sized sunshield keeps its instruments ultra-cold, crucial for capturing faint infrared light. JWST's mid-infrared instrument, MIRI, and near-infrared spectrograph, NIR spec, will analyze 32 Atlas across wavelengths from 0.6 to 28 microns. MIRI will capture thermal imaging and spectral data, while NIR spec will disperse light into spectra, identifying chemical signatures with 0.003 micron resolution. This combined analysis will reveal unprecedented details about the object. Post-perihelion observations are vital, as solar radiation exceeds 300 degrees X at closest approach, altering surface chemistry and vaporizing volatiles. Infrared observations will detect anomalies like unexpected outgassing or thermal hotspots, which could indicate active processes such as sublimation or cryovolcanism. Timing is crucial for tracking 32 Atlas's cooling phase as it moves away from the Sun. Rapid cooling may suggest a porous, low-density composition, while slower cooling could indicate a denser interior, hinting at a history of collisions or gravitational compression. This data will help unravel the object's origins and history, potentially linking it to events like the Late Heavy Bombardment 4 billion years ago. Observation. JWST's infrared images and spectra will provide the most detailed view of 32 Atlas yet. Comparisons with meteorite and celestial body measurements may reveal whether it is an asteroid fragment, a comet, or something more unusual. Detecting faint spectral features like the 3.05 micron absorption band of water ice or the 3.4 micron feature of organic compounds will be pivotal. Interpretation. Findings could reshape our understanding of small solar system bodies. Unusual chemical signatures or structures might challenge asteroid and comet formation theories. Unexpected organic compounds or hydrated minerals could suggest an outer solar system origin, while thermal processing evidence could indicate close solar encounters or collisions. Speculation. Some researchers propose that 30 Atlas is a remnant of a disrupted planet or an interstellar object given its unusual trajectory. While speculative, JWST's data will test these hypotheses. If the object defies conventional explanations, it could spark research into interstellar materials' role in solar system formation, illuminating the broader narrative of our solar system's evolution. Part 7. The Final Countdown. January 27, 2026. The UN exercise officially concludes. The global scientific community, which has been operating at a feverish pace, begins to slow its observations. Final data compilation and rigorous analysis commence. Final assessment. 2 full months after launch and 5 weeks after closest approach, the coordinated campaign ends. The comet 30 Seconds Atlas has been a constant presence in the skies, a celestial enigma that has captivated astronomers and the public alike. But now, it is a fleeting visitor, soon to vanish into the cosmic expanse. The final days of the exercise are marked by a sense of urgency and anticipation. Scientists work around the clock, poring over terabytes of data collected from every corner of the globe. Ground-based observatories from the towering peaks of Mauna Kea to the arid plains of the Atacama Desert have been tracking the comet's every move. Space-based telescopes, including the Hubble and the James Webb Space Telescope, JWST, have provided unprecedented clarity, capturing images and spectra that reveal the comet's composition, structure, and behavior in stunning detail. Yet, despite this wealth of information, many questions remain unanswered. Whatever conclusions can be drawn from 2 months of intensive global observation will be drawn here. The comet's trajectory, composition, and behavior have been scrutinized with unparalleled precision. But the comet will be dim, distant, and heading out of the inner solar system toward interstellar space. As it moves farther from the sun, its coma, the glowing envelope of gas and dust that surrounds its nucleus, will fade. Its tail, which has stretched millions of kilometers across the sky, will dissipate. Observation will become increasingly difficult as it recedes, its light growing fainter with each passing day. This is the end of our opportunity to study this object in detail. After this, 13 Atlas continues outbound, its journey through the solar system coming to a close. It dims, its once brilliant tail fading into the void. It recedes, growing smaller and more distant with each passing moment. Eventually, it becomes too faint for even the most powerful telescopes to track. It disappears back into interstellar space, a wanderer from the depths of the cosmos, and we never see it again. The comet's visit, brief but profound, will leave behind a legacy of scientific discovery and wonder. The final assessment will be a monumental task, requiring the collaboration of hundreds of scientists across dozens of disciplines. Teams will pore over spectral data, searching for clues about the comet's composition and origin. Did it form in our solar system, or is it an interstellar traveler, born in the cold depths of another star system? Its trajectory, hyperbolic and unlike any comet observed before, suggests the latter. If confirmed, 32nd Atlas would join Oumuamua and Borisov as only the 3rd known interstellar object to pass through our solar system. Yet, unlike its predecessors, 32nd Atlas has shown signs of activity, its tail a testament to the processes occurring on its surface. The comet's behavior has been equally puzzling. Its brightness has fluctuated in ways that defy easy explanation. Some researchers have proposed that these variations are the result of outgassing events, as pockets of volatile materials on the comet's surface are heated and released. Others have suggested that the comet's rotation may be chaotic, causing its brightness to vary as different parts of its surface are exposed to sunlight. Still others have floated more exotic theories, including the possibility that the comet's nucleus is fragmenting, breaking apart under the stress of its journey. The comet's color has also been a subject of intense study. Unlike most comets, which appear blue or green due to the presence of cyanogen and other compounds, 33 Atlas has a distinctly reddish hue. This coloration is thought to be the result of complex organic molecules on its surface, which absorb blue light and reflect red. Similar coloration has been observed in some Kuiper belt objects and centaurs, suggesting a possible connection between 3 Atlas and these distant icy bodies. However, the comet's hyperbolic trajectory complicates this hypothesis, leaving its origin a mystery. Status update. What we know. The UN exercise concludes on January 27, 2026. JWST will observe 32 Atlas post-perihelion, its infrared capabilities providing critical insights into the comet's composition and behavior. The final assessment will synthesize 2 months of data, drawing on observations from ground and space-based telescopes alike. The comet's trajectory, color, and brightness fluctuations have been meticulously documented, providing a wealth of information for analysis. What we don't know, what the final assessment will reveal. Whether the comet's anomalies, its hyperbolic trajectory, reddish color, and fluctuating brightness will be explained. What processes are driving its activity, and what this can tell us about its origin and composition. What happens after January 27th, as the comet fades from view and returns to the interstellar void? And perhaps most tantalizing of all, whether we will ever encounter such an object again, or if 33 Atlas will remain a singular enigma, a fleeting visitor from the depths of the cosmos. Part 8. The Scientific Debate. The debate surrounding 33 Atlas is unfolding publicly, in academic papers, interviews, and social media exchanges. The controversy centers on the interpretation of its periodic dimming pattern, which has sparked intense discussions within the scientific community and beyond. This debate is not confined to academic journals. It is a public, sometimes contentious dialogue with implications for how science communicates with the world. Harvard astrophysicist Avi Loeb suggests a 30–40% chance that 33 Atlas has artificial origins. He cites the precise heartbeat dimming pattern and unusual chemical composition, including unexpected traces of titanium and chromium, as evidence worthy of consideration. Loeb argues that science should remain open to extraordinary possibilities, even if they challenge conventional thinking. However, he emphasizes that these anomalies are not definitive proof. British physicist Brian Cox strongly dismisses the idea of artificial origins. He attributes the dimming pattern to natural phenomena, such as gravitational effects from a nearby exoplanet or an irregular dust cloud. Cox warns against sensational claims, emphasizing the need for rigorous evidence-based inquiry. He cites historical examples like pulsars, initially thought to be extraterrestrial signals but later explained by natural processes. The stakes are high for both the study of 30 Atlas and the broader field of astronomy. Loeb's hypothesis, if proven, could revolutionize our understanding of the universe. Conversely, Cox's skepticism underscores the importance of caution and rigor in scientific inquiry. The debate highlights a tension between openness to new ideas and the need for empirical evidence. Observation. The scientific community is divided. Researchers like Loeb argue for considering artificial origins due to the precise periodicity and unusual chemical composition of Third Atlas. Skeptics like Cox insist on natural explanations, emphasizing the need for extraordinary evidence to support extraordinary claims. Interpretation. This debate reflects a historical tension in science between bold speculation and careful skepticism. While Loeb's openness to unconventional hypotheses could lead to breakthroughs, Cox's caution ensures that science remains grounded in empirical reality. This interplay has driven scientific progress throughout history. Speculation. If Third Atlas is proven to have artificial origins, it would mark one of the most significant discoveries in human history, providing the first concrete evidence of extraterrestrial intelligence. If natural, it would still offer valuable insights into celestial bodies. The debate continues as researchers analyze data and engage in spirited discussions. The scientific community and the public are captivated by the possibility of an artificial object in deep space. This object has sparked a conversation that transcends science, challenging us to consider the possibilities of the universe. The debate has drawn experts from diverse fields, including astrophysicists, chemists, engineers, and philosophers. This interdisciplinary approach highlights the complexity of Third Atlas and the challenges of interpreting its behavior. Engineers have analyzed the mechanical precision of the dimming pattern, while chemists have examined spectral data for unusual elemental signatures. This collaboration underscores the importance of a multidisciplinary approach in tackling complex scientific problems. The debate has also highlighted the role of public communication in science. Loeb and Cox have been vocal in their positions, using interviews, articles, and social media to share their views. This openness has made the scientific process more accessible and engaging to the public. However, it has also raised concerns about sensationalism, with critics arguing that the media's focus on exotic explanations risks overshadowing the meticulous work of scientific inquiry. Balancing public engagement with scientific rigor remains a key challenge. As the scientific community continues to grapple with the mystery of Third Atlas, its impact on astronomy is clear. It has reminded us of the importance of curiosity, skepticism, and collaboration in the pursuit of knowledge, and inspired us to explore the vast and mysterious universe. Part 9. The Exomoon Hypothesis. A recent preprint proposes that Third Atlas might be a crustal fragment from an exomoon or exoplanet, challenging the idea that it is a primordial comet. This aligns with evidence suggesting exomoons, moons orbiting planets outside our solar system, are more common than once thought. Estimates propose that among every 200 planetary systems, one could host a potentially habitable exomoon. Kepler Space Telescope data has identified over 4,000 exoplanets, with some systems hinting at exomoons through gravitational effects. These moons, often overshadowed by their planetary hosts, could harbor environments shaped by tidal forces and internal heating. This theory addresses some of Third Atlas's chemical anomalies. Planetary crusts, formed over billions of years, contain metals and carbon dioxide locked in carbonate minerals, altered by tectonic and volcanic activity. For instance, Earth's crust is over 70% silicates, while Mars's is rich in iron oxides, reflecting distinct geological histories. The presence of such processed materials in 30 Atlas suggests it was part of a larger, differentiated body with active plate tectonics. Observation: 30 Atlas's surface is cratered, with some craters filled with solidified material. Spectral analysis detects silicates, iron and magnesium, common in planetary crusts. Infrared imaging reveals regions of varying thermal conductivity, inconsistent with typical comets or asteroids. Some craters appear resurfaced, suggesting past geological activity, possibly driven by cryovolcanism, as seen on Saturn's moon Enceladus. However, if 30 Atlas is a crustal fragment, why does it outgas? Rocks only release material into space when heated sufficiently to vaporize surface compounds, or when they contain trapped volatiles released by solar heating. One possibility is that 30 Atlas retains subsurface ice or volatiles from its formation, now sublimating due to solar radiation. Alternatively, outgassing could be driven by the release of carbon dioxide or methane, gases found in the atmospheres of geologically active moons like Titan and Triton. Speculation outgassing could also result from radiogenic heating, where radioactive isotopes generate heat, releasing trapped volatiles. This process contributes to the geological activity of moons like Jupiter's Io and Saturn's Enceladus. If true, 30 Atlas could offer insights into the geological processes of distant exomoons. The presence of short-lived radioactive isotopes like aluminum-26 could indicate 33rd Atlas originated from a young star system, where such isotopes are abundant. The exomoon hypothesis also raises questions about 33rd Atlas's origin. Its metal-rich composition suggests its parent body was geologically active and possibly habitable. The presence of carbonates, often formed through biological processes on Earth, hints at the possibility of past liquid water on its parent body, raising the question of whether such a world could have supported life. If confirmed, the exomoon hypothesis would redefine our understanding of interstellar objects. 13. Atlas would not just be a curiosity, but a messenger from a distant star system, carrying the geological history of an alien world. This challenges traditional classifications of comets and asteroids and underscores the need for further study of interstellar visitors. Studying 30 Atlas could provide insights into the origins and behaviors of these enigmatic travelers, like Oumuamua and Borisov. As researchers analyze 30 Atlas, the exomoon hypothesis will be tested. Spectroscopic studies will identify compounds associated with planetary crusts, and thermal imaging will map its internal structure. If evidence supports the idea that 30 Atlas is a crustal fragment, it could mark the first confirmed discovery of material from an exomoon, a milestone in the search for extrasolar worlds. Future space missions could intercept and study interstellar objects in greater detail, revolutionizing our understanding of the cosmos and revealing the stories of worlds beyond our solar system. Part 10. The Forensic Investigation. Astrometry, the precise measurement of celestial positions, is crucial in tracking the object. Observatories worldwide, from Mauna Kea to the deserts of Chile, photograph the object against background stars, measuring its position down to fractions of an arc-second. Data from these measurements allows NASA's Jet Propulsion Laboratory and the European Space Agency to model the object's trajectory with incredible precision. The stakes are high. Even a slight deviation could mean the difference between a near miss and a catastrophic impact. The object, now designated 3rd Atlas, moves at a staggering 30 kilometers per second, crossing the lunar distance, approximately 384,000 kilometers, in just over 3 hours. The Pan-STARRS Observatory in Hawaii and the NEOWISE Space Telescope provide critical data, revealing an object moving at approximately 30 kilometers per second. Its trajectory intersects Earth's orbit at an increasingly ominous angle. Every new measurement is a race against time to pinpoint the object's path. The Pan-STARRS system, with its 1.8-meter telescope and 1.4 gigapixel camera, scans the sky relentlessly, while NEOWISE's infrared sensors detect the object's heat signature, providing complementary data streams. The coordination between these instruments is a marvel of modern astronomy, with each observation refining the trajectory model. Photometry, the measurement of brightness over time, reveals the object's rotation rates, surface composition, and outgassing events. The Hubble Space Telescope and ground-based observatories like the Large Synoptic Survey Telescope in Chile monitor these fluctuations, generating terabytes of data daily. Each fluctuation is a clue to understanding the object's behavior and potential threats. The Large Synoptic Survey Telescope, now known as the Vera C. Rubin Observatory, will soon have the capacity to survey the entire visible sky every few nights, revolutionizing the tracking of near-Earth objects like 3T Atlas. On October 12th, Hubble detects a sudden drop in brightness, suggesting the object may have a companion or a cloud of dust briefly obscuring it. Scientists at the European Southern Observatory analyze the data to build a coherent model of the object's structure and dynamics. Misinterpretation of these fluctuations could lead to errors in predicting the object's trajectory, with catastrophic consequences. The European Southern Observatory's Very Large Telescope, with its 4 8.2-meter mirrors, provides unparalleled resolution, allowing astronomers to discern subtle changes in the object's appearance. Spectroscopy analyzes the light coming off the object to identify its chemical composition. The James Webb Space Telescope detects signatures of water, methane, and other compounds, providing insights into the object's origins and history. Ground-based observatories detect traces of iron and nickel, hinting at a rocky core beneath the icy surface. The object's composition defies classification, fueling speculation about its potential to harbor life or its remnants. The James Webb Space Telescope's infrared capabilities are particularly crucial, as they allow scientists to detect molecular signatures that are invisible to optical telescopes. Radio observations detect radio waves emitted by charged particles and plasma. The Very Large Array in New Mexico and the Atacama Large Millimeter Array in Chile map the object's interaction with its environment. These observations are critical for understanding how the object's trajectory might be influenced by solar activity. The data streams in real time, feeding into supercomputers that refine the models. The Very Large Array, with its 27 antennas spread across 36 kilometers, acts like a giant ear listening to the cosmos, while the Atacama Large Millimeter Array's 66 high-precision antennas provide unmatched sensitivity to millimeter and submillimeter wavelengths. The Very Large Array detects a faint signal indicating a magnetic field around the object, highly unusual for an asteroid or comet. The magnetic field complicates the object's interaction with the solar wind, potentially altering its trajectory in unpredictable ways. Scientists at the National Radio Astronomy Observatory work tirelessly to model these effects, adjusting their predictions as new data comes in. The magnetic field's presence suggests that 30 Atlas may have a history of interactions with other celestial bodies, possibly even a past collision that left it magnetized. All of this data is coordinated through IAWN, the International Asteroid Warning Network. Observatories share their findings in real time, creating a global web of information. Trajectory predictions get refined as more data comes in, narrowing the margin of uncertainty. Risk assessments get updated continuously, with teams working around the clock to interpret the data and advise governments on potential evacuation plans. The IAWN's infrastructure, built on decades of international cooperation, ensures that no observation goes unnoticed and no data point is ignored. At the IAWN headquarters in Vienna, teams of analysts process data from over 50 observatories worldwide. The information is fed into the Asteroid Impact Monitoring System, which continuously updates the risk assessment based on the latest trajectory data. On October 18th, the system calculates a 1 in 10 chance of impact, focusing the world's attention on the skies. Government agencies convene emergency meetings discussing evacuation protocols and civil defense measures. Amid the chaos, the scientific community remains steadfast, their focus unwavering. The Asteroid Impact Monitoring System, a sophisticated algorithmic tool, integrates data from optical, infrared, and radio observations to produce the most accurate predictions possible. Observation interpretation. The data reveals that 32 Atlas is not behaving like a typical asteroid. Its brightness fluctuations are erratic, suggesting it may be tumbling rather than rotating smoothly. Its spectrum shows unusual concentrations of volatiles, hinting at a composition more akin to a comet than a rocky asteroid. Radio observations indicate that its interaction with the solar wind is complex, possibly due to a magnetic field, a feature rarely seen in small celestial objects. These anomalies deepen the mystery surrounding 32 Atlas. The object's erratic brightness could also be explained by the presence of jets or plumes ejecting material from its surface, a phenomenon commonly observed in active comets. The object's tumbling motion is particularly concerning. A smoothly rotating object is easier to track and predict, as its behavior is more stable. But a tumbling object can exhibit sudden changes in trajectory that are difficult to anticipate. The presence of volatiles like ammonia and methane raises questions about the object's stability. As it approaches the Sun, these compounds could sublimate rapidly, creating a comet-like tail that interacts with the solar wind in unpredictable ways. The sublimation process could also release dust and debris, further complicating the object's trajectory and increasing the risk of fragmentation. Speculation. Could 32 Atlas be a fragment of a larger comet, broken off during a close encounter with the Sun? Or is it something else entirely, a rogue object from the outer reaches of the solar system? Theories abound, but one thing is clear. The more we learn about 30 Atlas, the more questions arise. Its trajectory, composition, and behavior defy easy classification, challenging our understanding of celestial mechanics and planetary defense. As the countdown to its closest approach continues, the world watches and waits, hoping that the combined efforts of the global scientific community will be enough to ensure our survival. The scientific community's vigilance is unwavering, but the stakes are higher than ever. Every new piece of data brings both clarity and new uncertainties, as humanity faces the prospect of a cosmic encounter with profound consequences. Part 11. The December 9th. Check-in, December 9th, 2025, marks the mid-campaign check-in for the International Asteroid Warning Network, IAWN. Over 50 observatories worldwide consolidate data to analyze the asteroid's behavior, just 10 days before its closest approach. Astronomers and analysts work relentlessly, surrounded by screens displaying real-time updates. The air is tense, filled with the scent of coffee and the weight of responsibility. This 10-day window is pivotal for evaluating the asteroid's trajectory and detecting deviations. Facilities like Arecibo Observatory and Goldstone use radar to measure the asteroid's shape, rotation and surface with precision. Arecibo's 305-meter dish and Goldstone's 70-meter antenna track the asteroid, forming the backbone of this global effort. Their instruments probe the asteroid's secrets from millions of kilometers away. The December 9th data uncovers a concerning detail. The asteroid's rotational speed has increased to 4.72 rotations per day, up from 4.69. Scientists recalibrate models to account for this variable. Even slight changes could indicate internal stresses or interactions with solar radiation, escalating the stakes. Interpretation. The rotational change may signal instability, suggesting the asteroid could break apart or shed debris. Even small fragments moving at high speeds could cause catastrophic damage if they enter Earth's atmosphere. The team now faces the possibility of multiple threats, each fragment tracked as a potential hazard. A 20-meter fragment could release energy equivalent to a nuclear explosion upon impact. Speculation. Could this change signal the Yorp effect, where solar radiation accelerates the asteroid's spin? If the spin intensifies, centrifugal forces could cause fragmentation. The Yorp effect, though observed in other asteroids, remains unpredictable. The team debates its potential role, their voices low but urgent. The room is quiet except for the hum of computers. Outside, the world remains unaware of the drama unfolding. For the team, December 9th is a turning point, a day of revelations and critical decisions. The asteroid has presented a new challenge, and the team must rise to it armed with science and the weight of humanity's future. Above them, the night sky stretches out, a reminder of the cosmic scale of their task and the fragility of the world they seek to protect. Part 12. The Observation Peak, December 19th, 2025. Closest approach. The comet will pass Earth at 0.048 astronomical units, about 4.5 million miles. While distant by human standards, this proximity is rare for astronomers. Telescopes worldwide will capitalize on peak visibility, with the comet shining as bright as a fifth-magnitude star. Amateur astronomers will set up tripods in frost-kissed fields, while professional observatories prepare instruments for an unprecedented glimpse. Every major telescope will be trained on the comet. Keck telescopes in Hawaii will analyze its light for water and carbon dioxide. The Very Large Telescope in Chile will capture images resolving surface features just dozens of meters across. Hubble will observe from above Earth's atmosphere, recording details with its advanced camera for surveys. Spectroscopy will be most detailed during closest approach, with up to 10 times more light available than during the comet's 2024 detection. Scientists aim to quantify its chemical composition, potentially identifying rare isotopes or organic molecules. Radar observations from facilities like Arecibo will map the comet's topography and probe its subsurface structure. At 1.5 arc-minutes across, the comet will be large enough for ground-based telescopes to resolve significant details, such as gas and dust jets or surface material disintegration. Some models suggest the comet's nucleus could be as porous as a snowbank, with voids and caverns that might collapse under solar heat. As the comet nears perihelion, solar radiation will drive off more icy material, revealing layers of its history. These layers could offer insights into the early solar system, when comets formed from planetary debris. Some theories propose that such comets delivered significant amounts of water to Earth billions of years ago. December 19th is the optimal observation window. The comet's tail could stretch tens of millions of kilometers, a spectacle unseen since the Great Comet of 1811. Its nucleus might reveal cracks or fissures hinting at its structural integrity. Any surprises, like unexpected outbursts or fragmentation, will likely occur during this period. Observation. The comet's behavior during closest approach will refine its orbital path and assess potential risks. Even slight deviations in trajectory caused by outgassing or other forces could significantly alter its future motion. Ground-based and space-based observations will track the comet with sub-arc-second precision. Interpretation. Data collected on December 19th will advance comet science and inform planetary defense strategies. Studying the comet's response to solar heating can improve models for predicting near-Earth object behavior, helping refine plans for deflecting or mitigating potential impact threats. Speculation. If the comet fragments, as some theories suggest, it could produce a spectacular display of multiple tails and nuclei. Fragmentation has been observed before, notably with comet Shoemaker-Levy 9 in 1994. While this comet is unlikely to suffer a similar fate, even minor fragmentation could provide valuable insights into the internal structure of comets. As the night unfolds, astronomers will watch, instruments ready to capture every flicker. The world will gaze upward in awe and curiosity, standing on the cusp of discovery as the comet reveals its secrets. Part 13. The Post-Perihelion Window. In late December through early January, the James Webb Space Telescope, JWST, turns its focus to Thruasakanu Atlas. Its infrared instruments detect surface temperature variations, chemical signatures, and structural features with unprecedented resolution. Positioned at the second Lagrange point, JWST's stability and 6.5-meter mirror excel at capturing faint infrared light, while its tennis court-sized sun shield blocks solar heat, allowing operations at cryogenic temperatures as low as 7 Kelvin. Post-perihelion observations are vital as the sun's heat alters the object's surface, chemistry, and structure. At perihelion, temperatures can reach 6,000 Kelvin, sublimating volatile compounds and exposing hidden layers. This natural process offers a brief glimpse into Thruasakanu Atlas's internal composition, providing insights into its formation and evolution. As it recedes from the sun, its surface cools rapidly, with temperatures dropping by hundreds of degrees daily. JWST's instruments will detect any unusual properties of Thruasakanu Atlas. The near-infrared spectrograph, NIRSpec, and mid-infrared instrument, MIRI, identify trace elements and compounds with unprecedented sensitivity. NIRSpec's spectral resolution of 0.001 microns distinguishes subtle chemical variations, while MIRI's operation at 7 Kelvin minimizes thermal noise. The near-infrared camera, NIRCam, will capture high-resolution images, revealing surface features as small as 10 meters. Observation. JWST's observations coincide with Thurston Atlas's recession from the Sun as its surface temperature stabilizes. This period is ideal for measuring thermal inertia, indicating the density and porosity of the object's material. Rapid cooling suggests a fine, loose regolith, while slower cooling indicates a more consolidated structure. Thermal emission curves will also reveal insights into its rotational period and axis orientation, critical for modeling its trajectory. Interpretation. JWST's data will be compared with ground-based observations and simulations to profile Thurston's Atlas. Spectral signatures will be matched to known materials in meteorite collections to infer its origin. The presence of hydrated minerals or carbonates could indicate past interaction with water, suggesting formation in the outer solar system. Their absence might suggest an igneous origin, implying formation closer to the Sun. Speculation. If Thurston's Atlas exhibits unique properties, it could challenge existing classifications of small solar system bodies. Its trajectory, with an orbital inclination of 32 degrees and an aphelion beyond Neptune, hints at an extrasolar origin or a dynamic history influenced by gravitational interactions. While unlikely, these possibilities underscore the importance of studying such objects to refine our understanding of solar system formation. The post-perihelion window lasts only a few weeks before Thurston's Atlas retreats into the outer solar system, where temperatures drop to 240 degrees C. JWST will operate continuously, gathering data for years of analysis. Each detail will deepen our understanding of Thurston's Atlas and inform future missions, reflecting humanity's pursuit of knowledge and the mysteries of these distant travelers. Part 14. The Final Assessment, January 27th, 2026. The UN exercise officially concludes. The sprawling network of observatories, research institutions and space agencies that had been tracking Thurston's Atlas for months begins to shut down their dedicated operations. Final data compilation. Final assessment. 2 full months after launch and 5 weeks after closest approach, the coordinated campaign ends. Scientists across the globe, from the icy plains of Antarctica to the tropical observatories of Hawaii, pack up their instruments and begin the painstaking process of analyzing the terabytes of data collected during the comet's brief visit to our solar system. The comet, now a faint smudge in the sky, has already traveled over 150 million kilometers from Earth since its closest approach. At this distance, it appears as little more than a distant pinprick of light, visible only through the most advanced telescopes. Whatever conclusions can be drawn from 2 months of intensive global observation will be drawn here. But the comet will be dim, distant, and heading out of the inner solar system toward interstellar space. Observation will become increasingly difficult as it recedes. The once brilliant object, which briefly outshone the full moon at its peak, now requires advanced tracking algorithms and long-exposure imaging to detect. Its tail, once a spectacle visible to the naked eye, has dissipated into a wispy trail, barely discernible against the backdrop of distant stars. This is the end of our opportunity to study this object in detail. After this, Thurston's Atlas continues outbound. It dims. It recedes. Eventually, it becomes too faint for even the most powerful telescopes to track. The James Webb Space Telescope, orbiting 1.5 million kilometers from Earth, captures the comet's final images before it slips below the threshold of visibility. Astronomers estimate that by March 2026, 13 Atlas will be indistinguishable from the background noise of the cosmos. It disappears back into interstellar space, and we never see it again. Observation. The comet's outbound trajectory provides one last glimpse into its composition. Spectroscopic analysis reveals traces of complex organic molecules, including amino acids and sugars, which were not detectable during its inbound journey. These findings suggest that interstellar comets like 33 Atlas could have played a role in seeding the early Earth with the building blocks of life. However, the data is incomplete, and the comet's rapid departure leaves many questions unanswered. Interpretation. The final assessment of 30 Atlas underscores the fleeting nature of interstellar visitors. Its brief appearance in our solar system highlights both the limitations and the potential of modern astronomy. While the comet's visit was short, the data collected during its passage will fuel research for decades to come. Scientists hope to use this information to refine models of comet formation, interstellar chemistry, and even the origins of life. Speculation. As 33 Atlas fades into the cosmic void, astronomers are left to wonder when, or if, another interstellar object will enter our solar system. Estimates suggest that such events occur once every few decades, but the unpredictable nature of these visitors makes them impossible to anticipate. The next one could arrive tomorrow, or it could be a century away. Regardless, the legacy of 13 Atlas will endure, a testament to humanity's enduring curiosity and our relentless pursuit of knowledge beyond the boundaries of our own world. Part 15. The Big Picture. 3Ti Atlas is the third confirmed interstellar visitor we've detected in 8 years. Oumuamua arrived in 2017, tumbling through our solar system with a trajectory and acceleration profile that sparked years of debate about whether it was a natural asteroid or something artificial. Its elongated shape, estimated to be at least 10 times longer than it was wide, challenged astronomers to explain its origin. Some theories even suggested it could be an artificial structure, though the consensus leaned toward a natural but highly unusual object. Borisov came in 2019, more clearly a comet, but still unusual in composition and behavior. Its tail, for instance, was highly active, releasing gas and dust at a rate far exceeding typical comets, hinting at a unique chemical makeup formed under conditions alien to our solar system. We've been watching the sky for centuries, charting stars, planets, and comets with increasing precision. And in all that time, we never confirmed an interstellar object until 2017. Now we're seeing them regularly. That's not because they suddenly started arriving. It's because our detection capabilities improved enough to spot them. The advent of advanced telescopes like the Pan-STARRS Observatory in Hawaii, which identified Oumuamua, and the development of sophisticated algorithms to analyze vast datasets have revolutionized our ability to track these cosmic travelers. These tools allow us to sift through the countless objects in our solar system and pinpoint those with trajectories that defy the gravitational influence of the Sun, the telltale sign of an interstellar origin. Interstellar space is full of debris ejected from other star systems. Rogue fragments from planetary formation, material blasted off worlds by impacts, all of it drifting through the galaxy, occasionally passing through stellar systems like ours. These objects are remnants of the chaotic processes that shape star systems over billions of years. For example, when planets form, gravitational interactions can fling leftover material out of the system entirely, sending it on a journey through the cosmos. Similarly, catastrophic collisions between planets or asteroids can eject massive amounts of debris into interstellar space, creating a slow-moving tide of cosmic flotsam. We're just now beginning to see that population, and every time we detect one, we're learning that our assumptions about what these objects are and how they behave need revision. Oumuamua, for instance, defied expectations with its non-gravitational acceleration, which some researchers attributed to outgassing, a process where trapped gases escape as the object warms near the Sun. However, no visible comet-like tail was observed, leaving the mechanism behind its motion a mystery. Borisov, while more comet-like, contained elements like carbon monoxide in unexpectedly high concentrations, suggesting it formed in a much colder environment than anything in our solar system. Each new detection adds to a growing body of evidence that interstellar objects are far more diverse and complex than we imagined. Their shapes, compositions, and behaviors challenge our understanding of planetary systems beyond our own. For example, the unusual trajectory of Oumuamua raised questions about the dynamics of its parent star system, suggesting it may have been ejected during a period of intense gravitational chaos. Borisov's chemical makeup hints at a formation environment rich in ices and frozen gases far colder than the outer reaches of our solar system. These insights not only expand our knowledge of the cosmos, but also inspire new questions about the processes that shape star systems across the galaxy. Observation. The increasing frequency of interstellar object detections is a direct result of advancements in telescope technology and data analysis. As our tools improve, so does our ability to identify and study these objects. Interpretation. The diversity of interstellar objects suggests that planetary systems across the galaxy vary widely in composition, dynamics, and history. Each object we detect offers a glimpse into the unique conditions that shaped its parent system. Speculation. As we continue to refine our detection methods, we may discover interstellar objects with even more unusual characteristics, further challenging our understanding of the cosmos. Some of these objects might even contain clues about the potential for life beyond our solar system, as they carry materials from distant star systems that could have supported habitable environments. In the grand scheme of things, these objects are more than just curiosities. They are messengers from distant stars, carrying stories of cosmic creation and destruction. Every detection is a reminder that our solar system is not an isolated bubble, but part of a vast, interconnected galaxy. As we study these interstellar travelers, we are not just learning about them, we are learning about ourselves and our place in the universe. Part 16. Planetary Defense. Planetary defense isn't just about detecting asteroids that might hit Earth decades from now. It's about being ready for anything unusual that enters our space. It's about having systems in place to rapidly assess threats, coordinate global response, and take action if needed. This isn't theoretical. It's a matter of survival. In 2027, the United Nations recognized the significance of planetary defense by declaring June 30th as International Asteroid Day, commemorating the 1908 Tunguska impact in Siberia, which leveled over 80 million trees across 2,150 square kilometers. The Tunguska event, likely caused by an asteroid or comet fragment, released energy equivalent to 10 to 15 megatons of TNT, demonstrating the catastrophic potential of such impacts. To prepare for these threats, NASA established the Planetary Defense Coordination Office, PDCO, in 2016, with an annual budget of approximately $150 million. The PDCO works closely with international partners to detect, track, and characterize near-Earth objects, NEOs, asteroids and comets whose orbits bring them within 48 million kilometers of Earth. As of 2023, NASA has identified over 28,000 NEOs, with more than 1,000 new discoveries each year. However, it's estimated that only about 40% of the 140-meter or larger NEOs have been found, leaving significant gaps in our awareness of potential threats. And increasingly, it's about dealing with objects we don't fully understand. If an interstellar object entered our solar system on a trajectory that posed genuine impact risk, we'd have very little time to respond. These objects move fast. They don't orbit the sun on predictable cycles. They pass through once, and if they're going to hit Earth, the warning time might be measured in months or even weeks, depending on when we detect them. For example, Oumuamua, the first interstellar object observed in our solar system, was discovered in October 2017 and had already passed its closest approach to Earth by the time it was detected. Its unusual shape, elongated and cigar-like, challenged existing models of celestial bodies and highlighted the need for adaptive observation and response strategies. That's why exercises like the one running right now matter. The International Asteroid Warning Network, IAWN, is refining its ability to quickly characterize interstellar objects, predict their trajectories with precision despite non-gravitational forces, and coordinate global observation even when the object is unfamiliar and behaving unexpectedly. In 2021, IAWN conducted a tabletop exercise simulating an asteroid impact scenario involving space agencies from 21 countries. The exercise revealed critical gaps in communication and decision-making processes, underscoring the need for more robust international cooperation. But preparation goes beyond simulations. In 2022, NASA's Double Asteroid Redirection Test, DART mission, successfully demonstrated the kinetic impactor technique, crashing a spacecraft into the asteroid Dimorphos to alter its orbit. The mission provided invaluable data on deflection strategies and highlighted the importance of early detection and intervention. Similarly, the European Space Agency's HERA mission, set to launch in 2024, will study the aftermath of DART's impact, providing insights into the internal structure of asteroids and improving our ability to model deflection efforts. The stakes are high. An impact from a 1-kilometer asteroid could release energy equivalent to over 1 million megatons of TNT, triggering global climate disruptions, widespread destruction, and potential extinction events. Even smaller asteroids like the 20-meter Chelyabinsk meteor that exploded over Russia in 2013 can cause significant damage, injuring over 1,500 people and shattering windows across the city. The Chelyabinsk event served as a wake-up call, illustrating the unpredictability of smaller objects and the need for enhanced detection and warning systems. Observation. The growing frequency of NEO discoveries and the unpredictable nature of interstellar objects underscore the urgency of planetary defense. While significant progress has been made in detection and deflection technologies, gaps remain in our ability to rapidly respond to unexpected threats. Interpretation. Planetary defense is not just a scientific endeavor, but a critical component of global security. The collaboration between space agencies, the development of advanced observation systems, and the testing of deflection technologies are essential steps in safeguarding Earth from catastrophic impacts. However, the success of these efforts depends on sustained investment, international cooperation, and the willingness to adapt to new and unfamiliar threats. Speculation. As our understanding of the cosmos expands, so too does the range of potential threats. The discovery of Oumuamua and the ongoing search for interstellar objects raise questions about their origins and the possibility of encountering more in the future. Could these objects be remnants of distant star systems or even artifacts of extraterrestrial civilizations? The unknown nature of such objects compels us to remain vigilant and prepared for scenarios beyond our current comprehension. Part 17. The Human Element. But there's another layer to this that doesn't get discussed as openly. Planetary defense preparation is also about maintaining calm. It's about demonstrating that institutions have plans, that systems are operational, that humanity has the capability to detect and respond to threats. This psychological aspect is critical, as public perception can often dictate the success or failure of large-scale efforts. For instance, during the 2017 close approach of asteroid Florence, NASA's public communication strategy ensured that the event was met with curiosity rather than fear. The asteroid, roughly 2.7 miles in diameter, passed at a safe distance of about 4.4 million miles. Yet the agency's transparency and proactive messaging prevented widespread alarm. Public confidence in preparedness reduces panic when something unusual happens. If 3 Atlas were approaching and no exercise had been announced, imagine the speculation that would dominate social media and news coverage. Is it dangerous? Is the government hiding something? Why aren't they doing anything? In the absence of clear communication, misinformation can spread rapidly. During the 2013 Chelyabinsk meteor event, the lack of immediate official statements led to a surge in conspiracy theories and panic-driven narratives. Within hours, social media platforms were flooded with over 500,000 posts, many of which were unfounded rumors about the meteor's origin and potential dangers. But because there's a visible, coordinated response happening publicly, those questions are diffused. Yes, we're watching it. Yes, we're coordinating globally. Yes, we have systems in place. Calm maintained. This coordinated approach is not just about optics. It's about building trust. During the 2021 close approach of asteroid Apophis, international space agencies collaborated to share data and reassure the public. The asteroid, once feared to be on a collision course with Earth, was confirmed to pass safely at a distance of over 10 million miles. This joint effort not only showcased global cooperation, but also reinforced the reliability of planetary defense systems. Observation. The psychological impact of planetary defense is as important as the technical aspects. When people feel informed and protected, they are less likely to succumb to fear or misinformation. For example, the European Space Agency's ESA Hera mission, set to launch in 2024, aims to test asteroid deflection techniques. However, the agency has also invested heavily in public outreach, ensuring that the mission's goals and progress are transparent. This proactive communication strategy is designed to build trust and reduce anxiety among the public. Interpretation. The success of planetary defense is not just about technology, but also about narrative control. Space agencies must not only detect and deflect threats, but also manage public perception. During the 2027 flyby of asteroid 1999 AN10, which will pass within 0.0026 AU, about 238,800 miles of Earth, agencies will need to balance scientific rigor with clear, accessible messaging. This asteroid, classified as a potentially hazardous asteroid, PHA, will provide a critical test case for both technical systems and public communication strategies. Speculation. As humanity advances in its ability to detect and mitigate asteroid threats, the role of the human element will only grow more complex. Future scenarios may involve not just deflection but also resource extraction from asteroids, which could introduce economic and geopolitical tensions. For instance, if a near-Earth asteroid like 16 Psyche, estimated to contain metals worth $10 quintillion, were to be targeted for mining, the public discourse would shift from fear of impact to debates over ownership, distribution, and environmental impact. In such cases, maintaining calm would require not just scientific expertise but also diplomatic finesse and ethical leadership. The human element in planetary defense is a delicate balance of transparency, trust, and preparation. As technology advances, so too must the strategies for communicating these advancements to the public. The stakes are high, not just for preventing catastrophic events, but also for ensuring that humanity remains united and informed in the face of cosmic uncertainties. Part 18. The Unknown. What happens if the January 27th final report documents that 32 Atlas had characteristics we can't explain with natural formation models? What happens if the data shows persistent anomalies that challenge our understanding of what these objects are? The implications could be profound, shaking the foundations of astrophysics and planetary science. Imagine the international headlines, the heated debates in scientific journals, and the sudden influx of funding into research programs tasked with deciphering the mysteries of these interstellar visitors. The stakes are high, not just for science, but for humanity's understanding of its place in the cosmos. One possibility is that scientists propose new natural formation scenarios we hadn't considered. Maybe there are environments around other stars that produce objects with composition and behavior we don't see in our solar system. For instance, the intense radiation and gravitational forces near pulsars or black holes could forge materials with exotic properties, unlike anything found in our local stellar neighborhood. Perhaps in the chaotic, high-energy environments of newly formed star systems, extreme temperatures and pressures could create objects with structural integrity far beyond what we currently understand. Maybe geological processes on exomoons create crustal fragments with unusual properties. These moons, orbiting gas giants in distant systems, could harbor unique geologies shaped by tidal forces, cryovolcanism, or intense magnetic fields. Such processes might produce objects with compositions and densities that defy our current models. Additionally, the interaction of these moons with their host planets could eject fragments into interstellar space, carrying with them the signatures of their alien origins. Maybe there are comet formation mechanisms in interstellar space that differ from what happens in protoplanetary disks. In the vast, cold expanses between stars, molecular clouds rich in complex organic compounds could give rise to comets with unusual chemistry. These interstellar comets, shaped by cosmic rays and the faint light of distant stars, might exhibit behaviors and structures that challenge our understanding of cometary formation. Their journeys through the galaxy could bring them into our solar system, carrying with them the secrets of the interstellar medium. New natural explanations that expand our models without requiring artificial origin hypotheses. That's the conservative scientific path, and it's probably where the consensus will eventually land, because natural explanations are always more likely than artificial ones. Statistically speaking, space is big, natural processes are common, and artificial objects are rare. The Milky Way alone contains an estimated 100 billion stars, each a potential site for natural processes that could produce objects like the Earth Atlas. The sheer scale of the cosmos makes natural explanations the most probable, even if they push the boundaries of our current understanding. But there's another possibility that can't be dismissed without evidence. Maybe we encounter something that genuinely doesn't fit any natural explanation we can construct. Maybe the periodicity, the composition, the structural integrity, all of it stacks up in ways that strain natural models past the breaking point. Imagine the moment when scientists around the world realize that the data points to something beyond the realm of natural phenomena. The shockwaves would ripple through every field of study, from astrobiology to philosophy, as humanity grapples with the implications of intentional design in the cosmos. Maybe the data forces consideration of intentional design. This is not a conclusion that would be reached lightly. Every possible natural explanation would be exhaustively tested, every alternative hypothesis rigorously examined. But if after all that the evidence still points to design, it would mark a turning point in human history. The search for extraterrestrial intelligence, SETI, would take on new urgency as scientists and policymakers alike recognize the potential for contact with an alien civilization. If that happens, it doesn't mean immediate confirmation of alien technology. It means the question gets escalated to more intensive investigation. Teams of researchers would pore over every detail of the object, using every tool at their disposal to unravel its secrets. Laboratories around the world would work in concert, sharing data and insights in a global effort to understand the object's origins and purpose. The scientific community would mobilize on a scale not seen since the Apollo program, driven by the possibility of answering one of humanity's most profound questions. Are we alone in the universe? It means resources get allocated to study the next interstellar visitor even more carefully. Governments and private organizations would invest heavily in new technologies and methodologies to ensure that no detail goes unnoticed. Observatories would be upgraded, spacecraft launched, and entire research programs dedicated to the study of interstellar objects. The global scientific infrastructure would be transformed, ready to detect and analyze the next visitor with unprecedented precision. It means SETI gets more funding because if artificial objects are passing through, we need to know. The search for extraterrestrial intelligence, long a fringe field, would suddenly become a priority. Telescopes tuned to detect signals from distant stars would multiply, their arrays scanning the skies for signs of intelligent life. SETI researchers, once marginalized, would find themselves at the forefront of a new scientific revolution, their work funded by governments and philanthropists eager to unlock the mysteries of the cosmos. Observation. The detection of an object like the Earth Atlas, if proven to be of intentional design, would reshape our understanding of the universe and our place within it. It would force a reckoning with the idea that we are not alone, that other intelligences share the cosmos with us. This realization would have profound implications for science, philosophy, and society as a whole. Speculation. If the Atlas or a similar object is confirmed to be of artificial origin, it raises the question of its creators. Who are they, and what is their purpose? Are they explorers, scientists, or something else entirely? And what would their discovery mean for humanity? Would it inspire us to new heights of achievement or plunge us into fear and uncertainty? The answers to these questions remain unknown, but the possibility of finding them is closer than ever before. The unknown beckons, and with it, the promise of discovery. Part 19. The Future. Whether 3 at the Atlas is natural or not, its detection marks a new era. Interstellar visitors are now regularly identified, with over 5,000 exoplanets and multiple interstellar objects, like Oumuamua and Borisov, discovered in recent years. This is not science fiction, but the reality of modern astronomy, driven by increasingly sensitive telescopes that capture data once unimaginable. Our observational capabilities have evolved to document these objects in detail. The James Webb Space Telescope, launched in 2021, can analyze exoplanet atmospheres for life's chemical signatures. The Vera C. Rubin Observatory, operational from 2024, will scan the entire sky every 3 nights, providing unprecedented data on transient objects, including potential interstellar visitors. These tools are more than technological advances. They are our windows into the cosmos. This era also marks a shift in how anomalies are treated. The detection of Oumuamua in 2017 sparked global debates that continue today. Was it natural, cosmic debris, or something more exotic? Such questions are now part of mainstream discourse, reflecting a collective mindset that embraces the unknown as an opportunity to expand our understanding of the universe. This progress signifies humanity maturing into a spacefaring species, attentive to its cosmic environment and open to the possibility of not being alone. In the coming decades, missions like the Europa Clipper and Dragonfly will explore Jupiter and Saturn's icy moons for signs of life, while private companies like SpaceX and Blue Origin aim to establish settlements on the Moon and Mars. These efforts are about exploration and survival, ensuring humanity's future beyond Earth. Observation. The rate of discovery is accelerating. From the first exoplanets in the 1990s to thousands today, and from theoretical interstellar objects to observed facts, the trajectory suggests even more remarkable discoveries in the next decade. These will challenge and refine our understanding of the universe. Interpretation. As our tools and methods improve, so does our ability to ask bigger questions. Are we alone? Is the universe teeming with life? These are no longer philosophical musings, but testable hypotheses within reach of our scientific endeavors. The future of astronomy is about redefining our place in the cosmos. Speculation. What if the next interstellar object is unmistakably artificial, a probe, beacon, or derelict spacecraft from another civilization? Such a discovery would revolutionize science and society, forcing us to confront a universe filled with intelligence and histories beyond our own. Even without such evidence, the search itself will transform us, pushing us to explore further, question deeper, and dream bigger. The future is not a destination, but a journey of discovery and adaptation. Whether third atlas is natural or something more, it represents a step forward. It reminds us that the universe is vast, complex, and full of surprises, and that our role is to keep looking, learning, and reaching for the stars. Part 20. The Promise. The contradiction that opened this story might never be fully resolved to everyone's satisfaction. Maybe there's no hidden truth, just different institutional perspectives on the same reality. Maybe there's more to the story that we'll learn later. Maybe the ambiguity is the point, the thing that keeps us watching and questioning and demanding better answers. After all, ambiguity has been the catalyst for some of humanity's greatest discoveries. It was the contradiction between Newtonian physics and Mercury's orbit that led Einstein to develop his theory of general relativity, a framework that not only explained the discrepancy but revolutionized our understanding of gravity, space, and time. It was the discrepancy between observed stellar motions and predicted models that led astronomer Fritz Zwicky to propose the existence of dark matter in 1933, a concept that remains one of the most profound mysteries in modern astrophysics. Ambiguity fuels curiosity, and curiosity drives progress. But one thing is certain. The countdown is running. December 9th is days away, a date that will bring the comet 32 Atlas within 0.28 astronomical units of Earth, close enough for even modest telescopes to capture its faint glow. On this date, the comet will be hurtling through space at over 100,000 kilometers per hour, a speed that defies human intuition. To put it into perspective, if you could travel at that velocity, you could circle the Earth's equator in less than 4 minutes. December 19th is 2 weeks out, marking the point where the comet will be optimally positioned for ground-based telescopes to capture high-resolution images of its surface. Astronomers are already preparing for this moment, coordinating observations across continents to ensure no detail is missed. On January 27th, less than 2 months away, the comet will reach perihelion, its closest approach to the Sun. At this point, solar heat will trigger the most dramatic outgassing events, releasing plumes of dust and ice that will stretch into a luminous tail millions of kilometers long. These dates are fixed, as immutable as the laws of celestial mechanics that govern the comet's trajectory. The information they'll reveal is coming, whether we're ready for it or not. And whatever we learn, it'll either confirm our understanding or force us to update it. Both outcomes matter. Confirmation is valuable. It strengthens our models and validates our predictions. For example, the successful prediction of Neptune's existence based on perturbations in Uranus's orbit in 1846 was a triumph for Newtonian mechanics, reinforcing the power of mathematical models to explain the unseen. But revision is progress. It's how we refine our theories, how we push the boundaries of knowledge. Every time we've updated our understanding of the cosmos, from Copernicus's heliocentric model to the detection of exoplanets in the 1990s, we've taken a step closer to grasping the truth of our existence. The promise of 33 Atlas is not just in what it confirms, but in what it challenges. Its unusual trajectory, its unexpected brightening, its potential to disrupt our current models of cometary behavior, all of these factors make it a target of immense scientific interest. So stay curious, watch the sky, follow the data, question the contradictions, and remember, the universe is stranger than we assume. It's a place where stars are born in nebulae that stretch light years across, where black holes warp space and time so intensely that not even light can escape their grasp, where entire galaxies collide in slow-motion dances that span billions of years. And sometimes, just sometimes, paying attention to the contradictions is how we figure out just how strange it really is. It's how we discovered that the universe is expanding at an accelerating rate, driven by a mysterious force we call dark energy. It's how we learned that light can behave as both a wave and a particle, a duality that forms the foundation of quantum mechanics. It's how we realized that there are more planets in our galaxy than grains of sand on Earth, each one a potential world waiting to be explored. In the vast expanse of space, a visitor passes through our solar system, leaving more questions than answers. But the questions themselves are a sign of progress. They show we're paying attention, that we're learning, that we're ready to revise our understanding when the data demands it. The Comet 32 Atlas is not just a celestial object. It's a test of our curiosity, our humility, and our willingness to confront the unknown. It's a reminder that the universe doesn't owe us easy answers, but it does offer us endless opportunities to ask better questions. The comet's journey through the inner solar system will be scrutinized by some of the most advanced instruments ever built. The Hubble Space Telescope, with its 2.4-meter mirror, will capture ultra-sharp images of the comet's nucleus. The James Webb Space Telescope, operating in infrared, will analyze the composition of its outgassing material, searching for organic